Today we're going to cover attribute and visual inspection, Gage R&R, if you will. We're going to discuss about the check inspector or the master inspector that will make a decision if the parts are acceptable or rejectable. And we're going to talk about the participant inspector. So let's say that we have a population of 250 good parts and 40 parts that are defective, and this data was qualified by check inspector or master inspector. Let's assuming that the same parts will be now inspected by participant inspector. We can see that the participant inspector identified 255 good parts and 35 defective. So now compared to the standard or the check inspector, out of this 255, only 46 parts were good and 31 defective, which is a true statement here. However, there are 9 good parts that were in fact defective parts according to the check inspector, and 4 additional parts which were labeled but as defective, they were in fact good parts. So this is not true, right? So we have 9 good parts were in fact defective, and 4 defects were parts labeled as they were good parts. In this particular case, we're gonna use some notation, GG, which will stand to, for true good and cold goods, and we're gonna have the GB, which is true good, but they were labeled as bad. And for the bad scenario, we have BG, which are true bad, but they were cold good. And also we have true bad and they are actually bad. For our particular case, you can see that we have GG, which are true, 246 parts, but 4 parts, GB, are false, and also BG, bad, cold, good, there were 9, so also this were false. And bad scenario, which there were 31 parts, so these are the true statements. So we're dealing here with two true statements, 246 which were in fact good parts, and 31 which were bad parts. However, we have 4 identified as good but they were bad, and also we have 9 that were bad but they were called as good parts. Let's now look at the proportion of good calls here. So this would be identified as GG plus a BB over the total number of units, in this particular case 290. So 246 plus 31 divided by 290. So this would be 277 over 290, and this converts into about 95.5% proportion of good calls. Let's talk about the consumer risk here, and this would be the ratio between bad, which are called goods, and also the total population of bad, if you will, which is a combination or total of bad plus bad cold goods. In this particular case, this would be 31 plus 9, and population or bad cold goods were 9. In this particular case, the consumer risk would be 22.5. Manufacturing risk, it's a similar scenario here, which is the ratio between good, which we were calling, which were in fact bad, over the total population of goods, which is GG plus GB. In this scenario, we have 4 parts which were good, but we call them bad, and the total population of goods, which is 246 plus 4. In this particular case, is 4 over 250, or 1.6%. Manufacturing risk, it's 1.6%. And again, we're reviewing here the consumer risk, which is 22.5%. Just a summary, as a consumer, we do not want to accept bad product, and also for manufacturing, we do not want to reject good product. So this is kind of the difference between consumer risk and manufacturing risk. In order to calculate repeatability, we need to have multiple trials, and also we have to ensure we have opportunities in agreement are not function of actual master. So for repeatability, we were not interested in an actual sample or standard, as we say. So again, repeatability, it's a ratio between opportunities in agreement divided by total number of opportunities. We will review later an example which will give you more vision of what this repeatability is. For attribute data, we also can calculate the bias, and we're going to need a table which I'm going to present later. And we talk about manufacturing risk and consumer risk. We calculate it. We have to look into a table to convert this into a bias number. So we're going to look up the BF manufacturing risk in a table. When in this particular case, this number would be related to 0.016 or 1%, 1.6%. BFMR would be 0.026, and for CR, looking up the table for the value of 22.5% or 0.225, we'll find a BFCR a value of 0.2966. So the bias would be the ratio between the two factors, and this turns out to be 0.0876. Let's quickly take a look at an example here. We have 3 trials and 1 operator for about 12 items. So you can see we have 12 items. And trial number 1, this column, trial number 2, trial number 3, and the actual where the master or check inspector, that if you will. So this would be your actual, and then we can reference this actual to the trial 1, trial 2, trial 3. In this particular examples, we have 12 units and 3 measurements, so we have 36 total data points. So if you review the data, you'll find out that we have 15 true goods, and we call them goods. We also have 3 goods which we call them bed, and also we have 4 beds that we call them good, and 14 beds which we call them bad. On the first column here, this will show you the total number of agreements. So in this particular trial, for part number 1, we have trial 1, 2, and 3 plus the standard, and you can see we have 3 agreements in place. For the part number 2, we have only 1 agreement, and this would be between the trial 2 and 3. We also have 3 agreements on part number 3. So I think you get kind of understanding how the number of total agreements will work. Again, if we add up total number of agreements in this particular example, you'll find out that we have a total of 26 agreements. So let's see how many total correct answers we have. We have all the good that are true, and we call them good, and the bad that in fact are bad, over the total number of inspection, in this particular case being 36. We have 15 GG, and we also have 14 BB. In this particular case, the ratio would be 81%, or if we turn around, we can also say that we have 19% error. The consumer risk, which is formula, we gave that formula previously, which is the ratio between BG divided by BB plus BG. So the total bed population is 18, and BG in this particular case, as you recall, it's 4, and the ratio would be 0.22 or 22%. Manufacturing risk, which is GB over GG plus GB, this would be 3 over 18 or 0.17 or 17%. Let's calculate the repeatability, which is the total number of good agreements over total number of opportunities. We have 26 agreements and 36 total number of opportunities. So repeatability would be 0.72 or 72%. Let's calculate the bias, and we talk about the table A9, and I'm just going to scroll down to this particular table just to give you an understanding. And this is a table. We talk about manufacturing risk of 17% and turns to have a bias factor of 0.241, and for consumer risk of 22% or 0.22, we have a bias factor of 0.2966. We will return now to the previous calculation, and plugging in those numbers, the bias would be the ratio between the bias factor for manufacturing risk over the bias factor of the consumer risk, and the ratio is about 0.86. Let's quickly review the indexes we calculated so far, which is C, the percentage of correct agreements, it's 0.81. Consumer risk as 0.22 or 22%. Manufacturing risk, which is 0.17 or 17%. Repeatability of 0.72 or 72%, and the bias is 0.86. Let's look quickly at this table. Sorry for a quick typo here, but we can look at acceptable limits for percent C. You can see that acceptance should be somewhere larger than 90. A marginal would be between 80 to 90%. Anything below 80% would be not acceptable. In our case, it's 81%, so we can say it's marginal. The consumer risk is 22%, and this number definitely is marginal. We also can see that the manufacturing risk 0.17 is unacceptable. Repeatability is not acceptable, but the bias of 0.86 appears to be acceptable because it's in the range of 0.8 to 1.2. Quickly, I'm going to present similar data looking in Excel, and the calculations which are pretty much done on this tab. So the data is on this spreadsheet, and the summary of some of the data that we show initially, it's on the other sheet. So remember, we have 29 of the total of 36 agreement, and this turns out to be about 80.5% accurate. And the error, if you look at 7 misses out of 36. It turns out to be about 19.44%. And the opposite, you can say, if the error is 19.44, then percent acceptance, if you will, is 80.6. So it's a complement, the balance up to 100%. If we look at good rated bad, we have 3 out of 18. If you remember, we had a population of 12 parts, and 6 of them were good and 6 of them were bad, just to make the example much simpler. So in our case, we had 6 good and 6 bad, and we measured those 6 good or 6 bad 3 times because we have 3 trials. So 3 divided by 18, which is our total sample for the 3 trials, you can see that number would be 16.66 good rated bad ratio, or we were 83.3% accurate. The error of bad rated as good, this would be 4 out of 18, or 22%, or accurate would be 77.8. If we look at the 12 trials, or 12 total number of parts were 12. From the totals, we missed 5 parts. Those 5 parts turn out to be the error of those 12 parts is 41% error, and acceptance would be 58.3, which is a kind of a low ratio of success. Let's use the filter option in Excel, and let's select just the bad standard. So these are the total of 18. You can see the count of 18. You can quickly look and see that there are 4 pieces mislabeled here in this scenario. If we flip the coin now and look at the good parts, we're going to select the good parts. Now in this particular case, there were 4 mislabeled, and there were 3 good measures, and we called them being bad by the same appraiser. Remember, we just have only one appraiser in this scenario. In this particular case, it's part number 11, part number 4, and item number 4 again. So from this perspective, we have item 4 and item 11. So there are 2 total parts being mislabeled, and we come back here, we gain more additional parts. So item number 12, number 5, number 2, and 12. So the totals, we miss about 5 items out of 12. So that's how we calculate the percentage, total percentage, which is a mixture between all 12 parts. Again, I'm just posting here the results of the accuracy, 29 out of 36 agreements. So we're 80.5% in agreement here, and this does not include the standard. This includes only looking at repeatability, and we're not interested in how the trials compare to the standard. Looking at the standard, we missed 7 out of 36. So looking at the standard, the error would be 19.4, and again the complementary would be 80.6% correct or acceptable. Manufacturing risk, we said we don't want to reject good products, so we rejected 3 good products out of 18. that will give us a percent error of 16.6 or 17% if you remember, or the percent acceptance in this particular case of good rated bad is 83.3. For the bad rated as good, we had 4 of those instances out of 18, or 22%. So this would be your consumer risk, and percent acceptance based on this criteria, 77.8%. From the total population, we misjudged 5 items out of 12, and the error would be 41.66%, or acceptance 58.3. We're switching over Minitab for a minute here. Minitab will perform the similar analysis, and this you can see, this is agreement assessment agreement, if you will. We had 12 inspected parts. We matched 7 out of 12, so we missed 5, and this means that we're 58.3 acceptance. Minitab does also calculate 95% confidence interval in this particular case, being 27.67% all the way up to 84.83. I'd just like to present how the data is published, or how it's done in Minitab. There are a few columns here. The appraiser 1, again this is just one operator. The 3 trials that we mentioned, the 12 items, the results in the standard or check inspector. This is a true answer for all the questions. Here is the results from the inspector. Let's look at how we can do an agreement calculation here. Going into Minitab, the quality tools, attribute agreement analysis, and you can see the results goes in attribute columns. The test item, where the parts are listed in a column, and the appraiser or the operator in this particular case won't make a difference since we have just one appraiser, and the standard, which is a known attribute standard, in our particular case the check inspector. We click OK, and this is a 58% calculation we mentioned within appraiser and appraiser versus the standard. And this is the session that we discussed here, the 41.67% error, or looking from the other angle, the 58% acceptance. So we match 7 out of 12, or we miss 5 out of 12. Now in Minitab we can use measurement system analysis for attribute Gage R&R, and we'll populate the field according to this example, and we will select here for the value of good acceptable items, the value good. That's how we call them here in the standard, good. Click OK, and Minitab will calculate automatically a lot of data. We can see the overall error rate, and again we've done this also in Excel, 19.4%. The good rated bad, 16%. The bad rated as good, 22%, and the mixture of rating, 41%. So remember, we missed 5 out of 12, so that's the percentage. The overall accuracy would be 1 minus 19.4%, when this particular case is 80.6%. It's kind of marginal from this perspective. Now the second graph calculates percent acceptance by appraiser. In this case it's 80.5%. Again, according to the standard, we can break it by goods and the bads and calculate percentages. Remember that 83 or 17% and 83%, the error versus variable of calling the good and the good beds, and the number for the bed, the percentage is a little bit lower, in this particular case being 77%. And the difference between the trials, so we had 3 different trials. You can see the percent acceptance on the trial 1 is 83%, on second trial 75%, and the third trial is 83% again. If we look at just the good calls, 83%, and the bad percentage is 77.7%. So all these calculations are similar regardless on how it's done in Excel or Minitab. Definitely Minitab will do a better graphics, and calculation would be a lot easier. Another reports from Minitab would be attribute agreement analysis for results misclassification reports. So now you can find out the percent of good rated as bad. We had an issue on item 4, so we probably call twice out of 3, 2 times out of 3, we call this item bad, or a wrong call, if you will. And for the item 11, so we can go back to spreadsheet, because we have them, we have those highlighted with different colors. Let's change this to good, and we can see item number 11. Item number 4 was called wrong twice, and item number 11 only 1 time. So this is what Minitab is saying. We have item 11, we have an error of 33%, which meaning that we missed 1 out of 3, and for item number 4 we missed twice out of 3. Moving into bed, percent bed rated as good, we have issues with item 12, item 2, and item 5, and we missed probably 2 out of 3 on item 12. Let's go back to Excel and validate this. I'm going to switch back the colors, and sure enough we have item number 5, 1 mislabeled, but we have item 12. We missed item 12 2 times, and I think we also missed item 2 1 time. And switching over to Minitab, yeah, item 5 and item 2 we missed once, and we missed twice on item number 12. So again, this is Minitab, a lot better interface, much easier performing this. At the end of the day, we want to make sure that our inspectors do agree between the trials. They have a small error rate, and we have a good repeatability. Very important how we select the parts. We want to ensure that we have a good combination between good and bad. Obviously, if we use all good parts, there is no need for a Gage R&R for attribute data, because we want to know that inspectors are capable of detecting the bad parts, or not rejecting a good product. So we want to minimize the consumer risk and also the manufacturing risk of rejecting good product, or customer risk of accepting bad product.